Okay, in the previous recording, we just showed that this set of functions, e to the I, 2n pi over big T, for all these n's, it's an infinite set of functions, one for each integer n. But we proved that this set of functions is orthogonal, and it's also complete, but you'll just have to trust us on that, so that we could expand a function using this orthogonal set. And when we did that, we came up with exponential Fourier series. This is the exponential Fourier series. This is how you compute the Fourier coefficients. One thing that's kind of confusing, it's almost a pet peeve of mine. You see f of x in two different places. This is the original function inside the integral. This f of x is the function that the exponential Fourier series converges to. It's this sum. Even though we use the same notation, they're not really the same function. I'll try to explain that as we go along. I'll show you pictures in a minute. For one thing, let's change the argument to x plus capital T, this same capital T. If I do that, I end up with this, and remember, e to the I 2 pi n is 1. I get the original function back. So if f of x plus t equals f of x, that means it's periodic with period capital T. So this f of x is going to be periodic with period capital T. This original f of x doesn't have to. Anyway, that capital T is called the fundamental period. So in hertz, the fundamental frequency would be 1 over T, and in radians per second, it would be 2 pi over T. And integer multiples of the fundamental frequency are called the harmonic frequency. Just some definitions. So here's what's going on. Here's the original function. This thing would go inside that integral. And let's say we're only going to, this is the interval we're looking at, from C to C plus capital T. So just from here to there. Without doing any calculations, you can draw the Fourier series, what it looks like, what the function that it converges to looks like. It will look just like the original function in that interval. So this from here to there is a duplicate of from there to there. But outside of that interval, you just get an infinite number of clones of that, each with period capital T. So all these guys are just the same thing copied. And any points of discontinuity anywhere, the Fourier series converges to the midpoint of the left limit and the right limit. That's what these little dots are here. And if the original function had a discontinuity, it'd be the same kind of limit. So it might not match the original thing perfectly in that interval, but it does where the original is continuous. So some key features of the Fourier series. Periodic, period capital T. It's going to perfectly match the original function everywhere the original function is continuous and in that interval. At points of discontinuity, it converges to the limit or the midpoint of the left and right limits. If the original function was periodic with period T, the Fourier series would match it perfectly everywhere where the original function was continuous. So this example, the original function is not periodic, but say it was just this part repeating. Fourier series converges to it everywhere except discontinuities. We define it for general, any place, any interval you want of length t anywhere along there. We're usually going to be working with symmetric intervals, and we'll call it from minus p to p, so that the capital T would be 2p. And you convert everything here, you get some new formulas for what exponential Fourier series looks like. Let's see, I think we got time for an example here. Let's say we have this, e to the minus x, defined only on this interval, minus pi to pi. So here's what the original function looks like. And we'll say it's only defined. Without doing any calculations, we know what the Fourier series looks like. It's going to look just like this function over the same interval. And outside that interval, it's clones of that original. At the midpoints or at the points of discontinuity, it converges to the midpoint of the left limit and the right limit. Let's actually compute that now. Here's the formula for it, right? That's how you get all the C sub n's. It's this formula. So we're just plugging that into the formula. Here's the formula. Here's the function. So, and it's from minus pi to pi. So those are the limits. Here's the function. In this case, p equals pi. So I just get nx there. So here's the integral we take. That's just e to the ax. I don't need a table or anything special for that. So I divide that, evaluate this thing between those two limits. I'll get this, that. I can factor out e to the pi. Actually, e to the minus in pi. Can't factor out anything just yet. I'll just factor them each. So this first term is e to the minus pi times e to the minus in pi. This guy is e to the pi times e to the in pi. But remember, e to the in pi plus or minus in pi was just minus 1 of the n. So now I can factor out the minus 1 of the n. I'm just left with e to the pi minus e to the minus pi. Actually, I switched terms and got rid of that negative sign. So that gives me to this. And here's where you can use some of your identities. You can recognize this as a sinh, as long as you have a 1/2 up here. So I'm making this 2, I'm bringing it, kind of separating it out. So that this part is just hyperbolic sine of pi. Here we go. We're almost done. We don't like complex numbers in the denominator. We get rid of them by multiplying by numerator and denominator by complex conjugate of the denominator. So I'll do that. And it simplifies a little bit. And finally, here is each coefficient, each C sub n. Fourier series, this was the formula. And it means this. Here's the C sub n's. And since p was pi, I get e to the I nx. I can pull out some things. Anything that doesn't involve n, because the sum is over n, I could pull it outside the sum. So here's the final, clean, simplified answer for the Fourier series. Here's the clean, simplified answer for the coefficient. The fundamental frequency is 2 pi over capital T. In this case, capital T was 2p, which was 2 pi. So the fundamental frequency here in radians per second is just 1. I think I'll stop there in this example. This was just using the formulas, but we did some simplifications that you probably wouldn't have been ready for if you hadn't already seen. like recognizing this kind of thing as a hyperbolic sign, getting rid of a complex number in the denominator. That was probably some new algebra you might not have seen before. We'll do more later.